Investigating Resistive Forces Video Lab by Marissa Hansen,
Alex Haber,
Ethan Phillips.
Our experiment investigated the question, how is terminal velocity affected when two styrofoam bowls have different surface areas or drop from the same height? We hypothesized that the styrofoam bowl that has a smaller surface area will have a higher terminal velocity due to less air resistance acting on the object. We changed the surface area of the bowl by removing the rim and placing it in the center. Both bowls were dropped from a height of 1 meter, and the chosen resistive fluid was air. Bowl 1 had a radius of 7 centimeters, and Bowl 2 had a radius of 6 centimeters. Tracker software was then used to analyze and compare the values of terminal velocity when the surface area was changed. The results of the average terminal velocities are shown below. Our system schema includes the earth and the styrofoam bowls that are being dropped, and the interaction between the two is caused by gravity. Our free body diagram shows a force of resistance from the air acting upwards on the bowl, and a force of gravity acting downwards on the bowl.
For our experiment, we needed to know the different types of air resistance in order to relate it to our terminal velocity. While our terminal velocity is the constant speed that an object is falling will eventually reach due to the resistance of the air preventing further acceleration. Drag is what we used, is proportional to the square of velocity, which is a type of friction that acts opposite to the motion of an object and resists the motion through a fluid. It is the air that is directly pushing against the leading edge of an object, while viscosity is proportional to velocity, a type of friction that acts opposite to the motion of an object. It creates more of a whirlwind motion in the back of the object, a motion where the object being squeezed through the air is passing through. The magnitude of the force of the resistive fluid of the object depends on its viscosity. Air has a low viscosity that is a liquid, such as water or corn syrup.
These models show a visual representation of drag and what it looks like when objects of different surface areas have air pass over them. On the image on the right, the object on the bottom has a large drag coefficient due to the fact that it is less aerodynamically favorable because of its shape and the way that air passes around it. Macroscopic friction is the interaction when one surface of an object is in contact with another surface. In our experiment, however, our bowl did not experience this type of friction because the entire surface of the bowl was in contact with the air.
So for this experiment, we used a camera, a meter stick, two styrofoam bowls, tracker software, and a laptop. What we did is we conducted the experiment by dropping two styrofoam bowls with different surface areas from a height of 1 meter. We recorded the movement of the bowls as they were being dropped with the camera and tracker software. The average velocity of the bowls was found by tracking the motion of it during the drop. Calculate the average velocity for each type of bowl from the two trials. The fluid used in this experiment that applies to a resistive force on both of the bowls with different radii is air. Terminal velocity is found using the formula given to the right, where m is mass, cd is the drag coefficient, P is the gas density, and A is the frontal area of the object. The ratio of the drag forces to the viscous forces can be found by the Reynolds number. And finally, the drag formula, which is given at the bottom, is directly affected by the surface area, pi r squared in this case, the frontal surface area, and changing the surface area would in turn change the drag on the object.
After completing our calculations, our results showed that the styrofoam bowl with a radius of 6 centimeters had an average velocity of approximately 1.8 meters per second, while the styrofoam bowl that had a radius of 7 centimeters had an average velocity of approximately 1.3 meters per second. We then concluded that the styrofoam bowl with a smaller radius did indeed have a higher terminal velocity.
This slide shows our results for our first bowl, our large bowl. The graph on the left is our first trial, and this one actually ended up being very good. Fairly good. As you can see, I end up with a pretty consistent-ish value after about 0.4. And the second figure also ended up with a somewhat consistent-ish value after 0.4.
So these are the results for our second size bowl, the smaller bowl. We ran two trials. The trial on the left shows that after about 0.4, shortly after that, it reached its terminal velocity, which is not as clear as it was in the first set of results, but still findable. And figure 2 also had about the same point, 0.4, except there's a spike very early on in the data. After looking back at the points, this was just considered to be an outlier. And we measured these graphs as velocity versus time.
We accepted our hypothesis that the styrofoam bowl with the smallest surface area had a higher terminal velocity. The variable that we changed and measured is surface area of the object that was being dropped while keeping the resistive fluid that it was being dropped through the same. When looking at two objects of the same mass, the higher velocity will occur in the object that experiences less air resistance, as shown through our data. And we kept the two masses the same to keep the force of gravity constant and only change the surface area. The extraneous variables and possible human errors should be taken into account when working with the software and materials. And we only recorded two trials, which means this data only applies in two cases. So there's potential for this data to be proven wrong.